We we are going to look a little bit more closely at exponential growth and decay rates. So to do that, let's just talk about a couple things. First of all, we want to make sure we understand that we see when growth of a function occurs when the base of that particular function is larger than 1. So that's something we talked about a little bit earlier. The other thing then is if we have a growth situation and we see a base, we can go backwards and find what percentage of growth that is. So this is looking at an equation or a formula. And so if we want to know what percentage that is, we take the base and we subtract 1 from it. That'll tell us that percent of growth. We also talked about this, that in a decay function, the base of the power is smaller than 1. It is larger than 0, but it is smaller than 1. And so if we want to find from that function, hey, what is that percent of decay? Like how fast is it decaying? We can take the base and subtract it from 1. So both of these allow us to go into looking at a formula and to find what those actual rates are. So we're going to do a few examples that involve that today. So this first example, it comes out and tells you that we have a function. We want you to go and identify whether it's growth or decay and then determine the percentage. So first of all, here we're going to then click on either growth or decay. And what we do is we look at the base to identify that. If that base is bigger than 1, this represents growth. If that base is less than 1, we'll say decay. So in this problem, it is growth. And since it is a growth problem, we're going to look from our previous page of notes. We then take the base, not this, just the base, and we subtract 1 from it. And that's going to give us this. This is now a decimal. We're going to convert that to a percent. So we're going to do two things. You can either multiply by 100, or what you can do is you can move the decimal 2 spots. This is a growth situation that represents a 95.8% increase. Okay. So this is one example. Now we are going to switch up the equation a little bit. So sometimes the equation might look like this. This one looks quite a bit different. So in this particular problem, in order for me to identify the base, I need to separate this exponent here. So I would rewrite this as 2 to the power of -4 to the power of x. I want to separate it so I can identify what that base actually is, because that base might be in disguise a little bit here. Now from our algebra 2, this negative exponent is 1 over 2 to the 4th to the power of x, which is we can write, well, let's just write this like this first, 1 over 16 to the power of x, which approximately, if we type that into our calculator, we are going to get 0.0625 to the power of x. And so we're really just looking at this value here. Since that value is less than 1, we say that this is a decay problem. So let's go up here, decay. And to find then what the rate is, we're going to take 1 minus that value. That's the base. Which, if we round then here, we get 0.9375. We run around to the nearest tenth of a percent, or more, 93.8%. Either multiply this by 100 or we're just moving the decimal places. This problem right here looks a little bit different. We got a couple things going on here. We have a number in front of the base. The base of this exponent is a little bit tricky. We want to separate these exponents here. So this is going to be 700, and let's use some parentheses here. E to the power of 0.0. Ooh, geez. Hold on a second here. 0.27, and we'll separate the exponent here. And the reason why we want to do that is now our base is right here. The 700 is not the base, so we don't really want to look at that. We just want to look at that e to the power of 0.27. I'm going to use my calculator on that. Remember, we're not estimating e. So when we find this, I'll pull my calculator into view here. We want to make sure we're using this e to the power of 0.27. So let's clear this. I'll show you my keystroke history here. Maybe I won't. Let's see. Oh boy. Let's clean this up a little bit. Okay, so we're going to go E. Sorry about that. Second negative sign, and then we'll go power. Oh boy, try that again. Second division symbol. All right, there's my E. And then we'll go power 0.27. Right? This is going to be our base, the 1.3099. And let's just look back up in the directions there. It says just determine the percentage rate of increase equals to the next to the nearest tenth of percent. So let's just let's use a few more decimals here. So let's use we'll go so this is still 700. We don't really care about that. But this base is really the number we care about. 1.30996 to the power of x. Because this value here is larger than 1, this definitely represents a growth situation. And because it's growth, we're going to take that value and we're going to subtract 1. This is going to allow us to identify the rate. So I get 0.30996. Want to round to the nearest tenth of a percent. This one's kind of tricky. So if I move this decimal, it would be 30.996. The nearest tenth of a percent is here. So that number is a 9. It moves this 9 to a 0. And it moves this 0 to a 1. So this is approximately 31.0%. 31.0%. Hey there, I'm going to show you how in this example, we're going to find two things. We're going to write a function after t years, basically showing the value of the account, where we have something called the annual growth rate. In that function, we want to make sure we round all coefficients to 4 decimal places. And then after that, we're going to just determine a percentage of growth, which is also called an APY. So it's per year to the nearest hundredth of a percent. All right, so this is kind of exciting. So basically what I'm going to do is I'm going to look at this problem. We start with 620. 620 is what we write right here in the beginning of the function. And then in these parentheses here, what I'm going to do is I'm going to save this for now because I got to do a little bit of math. So my function, I'll write it down here, after time t equals the original amount, which is 620, and then the formula goes like this. It's 1 plus, we're going to take this percentage right here. We're going to convert it to a decimal, 0.055. We're going to divide it by this number, 365. So if it says daily, that's 365 times. And then my exponent is 365 multiplied by t. Now what I need to do here is I need to simplify this so that this base is a single number And the exponent is just t. So I want to get rid of this 365 as an exponent. I want to simplify this fraction, add it to 1, and then I'm going to get a number down here. That number is what's going to go in here. And then time is up here. So to do that, I'm going to have my calculator. Here's the steps that I want. And I don't want to round until the very end. So I'm going to start way on the inside, right in here. I'm going to start with that number. So 0.055. I'm going to divide that by 365. I'm going to figure out what that value is. You can see that value is irrational. Well, it's actually just so small to use the scientific notation. Okay, but I want 1 plus that number. So I can reverse the order here, plus 1. So answer plus 1. So that's this base right here. I'm just going to rewrite this so you see this. So this is 620 times 1.0. Do not round yet. 0.0150685. And then my exponent is 365 t. What I can do here is I can simplify this to make this look like this: 1.000150685 to the 365 power to the t. I can break this up right here, and this is important to do. Break this up so it's in terms of t, which gives me what I call the APY, annual percentage rate in a year. So I just need to figure out what this value is to the 365. And on my calculator, I already have it up here. And so I'm just going to go exponent 365, hit enter. There's the value. I want to go to 4 decimal places. So that's the value that goes right in here, 1.0565. 4 decimal places, 1, 2, 3, 4. All good. Now, a couple more things. This is what we call growth rate, because this number is larger than 1. Now, to find this percentage here and to submit my answer, the reason why it's 5.65% is this number right here. It's growth. So I take this number minus 1, and I get 0.0565. Convert that to a percentage, 5.65%. There we go. So the key to these problems is once you set it up here, simplify the base, get it to here, raise the base to the power of 365, so separate these exponents, and that'll get you your base in terms of t. This is exciting. Here, very similar, a couple differences. The differences are that it's compounded continuously. We do use a different formula for that. Again, look back in your notes. That's our first step. We want to make sure we round all the coefficients to 4 decimal places. Okay, so if we look back in our notes, our formula is A equals our principal multiplied by E, and now my exponent, and this is E is the base, my exponent is the rate multiplied by time. Okay, so let's separate a couple things. Let's to find what this is per year. I'm going to try to separate this exponent. I'll show you what that will look like. So this is still my principal. Let's use some parentheses here. So this is e to the 0.081. We're separating that from t. E to the 0.081. Again, let's use your calculator for that. That is 1.0844. Okay, now that I have computed that on my calculator, I want it to 4 decimal places. That's right here, 4 decimal places. That allows me to see that this is a growth situation. I've isolated the exponent so that this is a yearly problem. First step is I'm going to write, this is my function or my formula. Now to find what it is, remember I take this value, the base, and I subtract 1 from it. And then what I want to do here is just write it as a percentage to the nearest tenth of a percent. 8.4, is it nearest tenth? Nearest hundredth, my bad. 8.44%. There you go. Good luck.